next speaker that we have is Julia, also from Klima. And we heard a little bit about ocean now, we heard a little bit about ice and about atmosphere, and guess what's coming next? The coupling of the three.
Hello, everyone. I'm Julia, the person, not the language. And today I'm going to be talking about ClimaCoupler, which is the component of this undertaking Klima, which, as Milan said, couples together these different component models that we've heard a little bit about today. So just as a brief background, I won't get too into detail about this since we've been talking about Earth system models already for a while now. But an Earth system model is a model of our planet that typically includes multiple different component models. So this could be the atmosphere, ocean, land, and the cryosphere, such as the sea ice that Skylar was talking about. And we have all of these different component models, but we also want to be able to link them together in some way and have them really fully represent the entire planet, which consists not only of one of these components, but of all of them. So this is where the coupler comes in. So before I get into the coupler, I'm going to give a little bit more background about CLIMA. So CLIMA stands for the Climate Modeling Alliance. And this is a project that's being worked on by collaborators at Caltech, MIT, JPL, and a few other collaborating institutions. And our goal is to build a new Earth system model from scratch in Julia. And there are many existing Earth system models, but a lot of these models, while they're very powerful, they're based on legacy code that was written in Fortran as early as the 70s. So we're really trying to develop a new model that makes use of recent technological advancements as well as newer climate science to make a more accurate and performant model. So here's an overview of the CLIMA structure, just to give you an idea of kind of how, kind of the scope of the project. So I'm going to be talking about just one of the packages involved in this project, ClimaCoupler, but there's a whole host of packages involved. These you can see some are for the atmosphere, some for the land, some for the ocean, and then some utility packages as well. And there are even others that aren't pictured here. So it's a pretty complicated, interconnected web of Julia packages that we're developing. So as I mentioned before, we have these Earth system models which are made up of multiple different component models. And the role of the coupler is to connect them between each other, kind of to allow them to speak to each other. And there are sort of three main challenges that the coupler faces in doing this. The first one is exchanging information between the components, so typically exchanging fluxes between different component models. And it also has to deal with different discretizations in space as well as time, because the component models aren't necessarily using the same discretizations, and we have to be able to kind of reconcile these differences. So now I'm going to go into each of these challenges a little bit more in detail. So the first is this exchange between component models. So here I have a diagram showing a simple atmosphere model and an ocean model and just some of the quantities that are involved with these different models. So we have some quantities that are computed internally to each of the models. So for example, we have precipitation. This is a quantity that will be computed inside of the atmosphere model, but at some point this precipitation is going to move through the atmosphere and hit the surface of the ocean. And so at that point, this water, you can think of it as like a mass balance situation where this water mass is going to have to exit the atmosphere simulation and enter the ocean simulation. And so this is where the coupler comes in. It kind of handles this flux of water moving between the atmosphere and the ocean in this example. There are also other quantities that are similar, such as surface temperature. This is a quantity that affects both of the component models, and we have to make sure that it's that they're kind of coordinated, as well as we have radiative energy flux and albedo. These both play a big role at this surface between the component models. We also have slightly more complicated fluxes, such as turbulent fluxes, which rather than being computed internally to one of the models, they depend on quantities that exist in both of the models. So this could depend on velocities of the air in the atmosphere, the water in the ocean, as well as roughness lengths of both models. So some of these fluxes become more and more complicated to calculate. And again, the role of the coupler is to make sure that both models are kind of on the same page and are exchanging this information accordingly. So the next challenge that the coupler has to address is spatial discretization of the component models as well as regridding between the component models. So here we have two examples of cubed spheres. So since our simulations are being done on for the globe, for the entire planet, they're done on a sphere. And to be able to do computations on the sphere, we have to discretize it, typically into grids. Although, as was mentioned before, this could be any other type of discretization, including like triangular grids, something like that. But right now we're using cubed spheres, so these are just a couple of different options. Each has their own pros and cons, but I won't get into the details of that right now. And here's a simple example where you can see two different meshes that two different models could have. So you could think of model 1 being the atmosphere and model 2 being the ocean, and they each have these different meshes. And even though they're on different meshes, they still want to be able to communicate with each other if they're being coupled together. So the red dots here are nodes where we could have information actually being evaluated, and these are the points where we have data that needs to be transferred between the two models. So you can think about if we're moving from the coarser resolution mesh to the finer resolution mesh, we have to perform some kind of interpolation to get this higher resolution data. And vice versa, in the other direction, we have to make sure that we're sampling the correct data points to correspond to the points in space where model 1 is being evaluated. Now, this is kind of a simple example because the meshes are co-located with each other and they're also the same type of mesh. But we could have more complicated examples if the meshes were different types of meshes or rotated with respect to each other. And all of these kinds of variations make this a more and more difficult problem to solve. The next challenge faced by the coupler is temporal discretization. So this really only comes up in our coupler because our coupler also serves as the driver for the coupled system. But if the coupler was separated from the driver, this would be more related to the driver, but I'm talking about it because it does come up in our coupler. So the idea here is that we have multiple different models that need to be time-stepped, and there are different approaches for doing this. So this first diagram is showing explicit coupling. So we have an atmosphere model and an ocean model, and the first thing we do is we initialize both of them. And in this approach, we first exchange information between both of the models before stepping either of them. And then we step both models, and again, we exchange information, and then step again, and so on. And one advantage of this kind of approach is, first of all, it's pretty simple to implement compared to other time-stepping schemes. It also has the ability to be concurrent, so you can step both models concurrently, or you could step them sequentially, but stepping them concurrently is faster because it's parallelized. But this is not the only approach to time stepping that we have. So another option is leapfrog coupling. So this starts off similarly. We have our two models and we initialize both of them. But in this approach, we take, at the beginning of our simulation, we take our information from the ocean and we send the fluxes that we need to communicate to the atmosphere first. And then we take one time step of only the atmosphere model. And then we send these updated fluxes from the atmosphere to the ocean model, step the ocean model, and continue in this fashion. So a downside of this is that this can't be done concurrently because we kind of need to step them in this leapfrog pattern. And so this can't be done at the same time. But an advantage is that at each time step, the ocean model is getting kind of like these updated fluxes from the atmosphere. And so this prevents the fluxes in each of the models from diverging, which is something that you can encounter with, say, explicit coupling if you have a very large time step. So I'm going to discuss a little bit about existing couplers and what we're hoping to achieve with our coupler. So there are two main types of existing couplers in use today. The first are model-specific couplers, which are often written with a specific component model in mind. And because of this specificity, they can be a little bit more hard-coded, just because they're designed with a specific model as the end goal. We also have these more widely used community couplers, which are often very powerful and very general, able to be used with different types of component models, even if these component models aren't designed with this coupler in mind. And so this is a very useful trait to have. We want to be able to reuse this code over and over rather than having to redesign a different coupler for every component model that gets written. So while these couplers are very powerful, one downside is that they can become very complicated internally. For example, if you're connecting different component models that have different functionality, different fluxes that they require, you're going to have to keep on adding additional functionality to the same coupler, and it can become kind of a conglomerated, huge piece of software. So the goal for our coupler is to be simple, like a model-specific coupler, but also adaptable and general, like a community coupler. So since we're at JuliaCon, I'm going to get into a little bit of how Julia plays a role in this. So one of the benefits of Julia that's been really helpful in our development of the coupler is multiple dispatch. I'm sure this is one of our favorite features of Julia for most people here. So the coupler has kind of a unique role in that it has to specify this interface that each of the component models must implement. So we try to keep this interface as general as possible and as slim as possible, but there are a couple of functions that we just need these component models to provide. So one of these is a step function. We need to be able to step each of the component models. We also have some getter methods to retrieve fluxes that will need to be sent between the models. And multiple dispatch is very helpful for this because we can write these functions and explain that these are the interface, and then new users can come in and just very easily add new methods for these functions and extend them without having to change our source code at all. And you can see here that we have the step model sims function, which steps all of the component models in our simulation. And due to multiple dispatch, this function is very simple. So all we do is we have this simple for loop that loops over all of the component models, and then we call this step function on each of them. And since each of the component models has to have this step function defined, this will just dispatch off of the type of the model, and we'll step each of the component models. Something else that Julia has been really useful for is performance, both in terms of tracking performance and improving our performance. I wanted to shout out a couple of packages that have been really useful for us. The first is profile.jl, which is useful for visualizing memory allocations. And the second is flamegraphs.jl, which shows how much time is spent in each function. And these both really allow you to kind of target where your code is maybe not optimized. And you can kind of further dig into those and improve the code there. And we're also very happy that Julia is GPU compatible. As you heard from Greg earlier, Oceananigans is running on GPUs, and they had significant speed up when they made the switch from CPU to GPU. So we're currently in the process of rewriting, well, not rewriting, but going through our Atmosphere code and making sure that it will be GPU compatible with the hope of hopefully running it soon on GPUs. Unfortunately, we've also encountered some problems with working in Julia. You know, no language can be perfect, so one of the issues that we face as the coupler is that we're downstream of many packages. We're downstream of all of the component models as well as everything that they depend on. And so this can lead to longer pre-compilation as well as difficulties. If any of these packages makes a new release with any breaking changes, we have to kind of go through all of the packages that depend on that. There's a lot of interdependencies in our web of Klima packages. So we kind of have to go through and update all of the packages that depend on this one that had the breaking change and make sure that everything is compatible. But at some level, this is kind of inevitable when you're working on code that's still in development. So it's not necessarily something specific to Julia. And another point is that Julia is a younger language, and so there's not as much developer support as we might have in some other languages. For example, we had to develop our own ODE solver package, Klima time steppers, because while we were using ordinary diffie-q for a while, it ended up not having all of the functionality that we needed. So we're kind of extending it with this new Klima time steppers package. So now just a little summary to recap. We have some of our challenges that we're undertaking here. For our regridding, we currently support certain mesh types, and we're working on extending it to support even more general additional types of meshes. For our time stepping, we've implemented explicit or leapfrog schemes, and soon we're going to be working on concurrent time stepping. Our interface is currently pretty sleek and slim, largely thanks to Julia's multiple dispatch, and soon we'll be testing it with additional models we hope to soon couple to Oceananigans in the coming months. And in terms of performance, we've been able to really easily assess our performance, and we're currently working on getting our Atmosphere code to run on GPUs, which will hopefully significantly speed up our code. And with that, I'd like to thank my coworkers in Klima as well as our funders, and I'll take any questions you have. Yes.
Oh,
I don't know.
you can repeat my question.
Okay.
I assume the atmospheric models being discussed here focus on the troposphere. Has there been much research into interaction between, I'll just say the question, has there been much research into interaction between the troposphere and higher layers of the atmosphere like thermosphere and ionosphere?
That's a really good question. So the question is, I guess you had the microphone, so I don't have to repeat it. I guess I don't work on the atmosphere myself. I work mostly on the coupler and the land model, so I'm not exactly sure. I don't think I can answer the question.
You mentioned that you were initially using ODE.jl, but it was missing some functionality. What was missing?
Yes, this is a good question. Simon may know.
Sure. I'm really just curious.
So I think the reason for multiple things, it tries to do a lot of things which we don't need, and it wasn't quite as extensible as we needed it to be to do the things we wanted to do, particularly the distributed pieces, to reuse data, like, to minimize the amount of memory you're reusing. And you could get it to work, you could monkey patch it, but then everything would break when they bump versions. And then yeah. Yeah, and I think, I mean, well, I mentioned this as well, is that you end up using, there's a very small subset of time stepping schemes you end up using, and you often need to do weird things like project, there's often like a bunch of fixes you have to throw in there to make them, stable or keep you within some fixed domain or positive preserving and positivity or something, yeah. That was the crux of it, I guess. Yeah.
Hi, first I just want to say that was a great talk. Second of all, what happens for concurrent time stepping if you have two time steps where the least common multiple is a really large time step? And how would you deal with a problem like that?
Yeah, that's a really good point. So yeah, I think you mentioned the least common multiple because the naive approach is just to run both models for the amount of time that is the least common multiple of their individual time steps. And it's important to note here that each component model has its own time step, and the coupler has like a separate time step in terms of like the number of seconds or hours or whatever you're running the model for. So there are a couple of different approaches you could take here. One of them could be to, let's say you have one model that runs for 7 hours and one that runs for 11 hours. So the least common multiple here is pretty large, and you wouldn't really want to run your models for 77 hours independently. So what you could do is run the shorter model for 7 hours and then do a shorter 4-hour time step, and then run the second one for 11 hours and then reconvene kind of at that 11-hour mark. But I'm sure there are other approaches that you could take as well. That's just the first one that comes to mind.
I have a question on let's say the general philosophy of whether does the atmosphere and the ocean, do they depend on the coupler, or does the coupler depend on the atmosphere and ocean? Which is kind of obviously things where you have to, talk to each other as well, right? But in the end, do you want to make the coupler so extendable that other atmospheric models can, so that the coupler can be used also with other models? Or do you want to flip the whole philosophy around and say this is what the coupler defines. If you want your atmospheric model to work with it, you have to follow these rules that the coupler sets.
Yeah, this is a really good question. This has actually been a point of discussion recently. So I've been presenting about ClimaCoupler, but we're also working on kind of a new and improved coupler, which will be called ClimaEarth. And sort of, I think the design that we've settled on, at least in this moment, is I mentioned before that we have our coupler and we also have the driver as part of the coupler, which is maybe sort of not the approach that you need to take. It's kind of a design choice that we've made. And so because of this, the coupler is dependent on each of the component models. But if we make this design that we're moving towards in the future, what we'll have is this ClimaEarth coupler that, like I said before, it provides the interface for the component models. The component models will depend on this ClimaEarth package and extend each of these functions that it provides. And then we'll have some kind of separate script that takes these functions together and actually runs them.
There's been another type of Earth model that's been presented at this conference, and those are the Earth economic resource models that predict population trends, pollution, et cetera. So the limits to growth studies from the 70s were based on those models. Has there been much thought or effort put into coupling your high fidelity physics models from the ClimaCoupler effort to those economic resource models from that other effort?
That's a really interesting point. I haven't heard any talks about our intentions to do this in the group. I think since we're still in development, we're kind of not at the stage yet where we're talking as much about like applications and like specifically what use cases we'll apply this to. But as we get closer to having a fully working model, that could be something that we consider.
What's been one of the most interesting or difficult pieces of working on the coupler?
Yeah, thank you for the question. That's an interesting point. I think, at least in terms of difficulty, one of the things that I've been working on lately is taking this regridding and making it distributed. And so this becomes pretty complicated because we're trying to do this with MPI, but I guess it's, in theory, it's not too difficult. We can kind of talk about how to do it and come up with a plan for it, but then once you get into the nitty-gritty details, it has become actually a little bit difficult to implement. So I would say that that's something that has taken up some of my time recently.
Could you speak more about what I think you called the community coupler, which is a generic software for, if I understand it, coupling generic physics models? And I guess I don't understand that because I would think the coupling between the atmosphere and the ocean depends on one kind of physics and and the coupling between precipitation and the ocean is something else. Maybe I'm missing what a community coupler is.
Yeah, I can expand on that a little bit more. So these community couplers, even though they're like a more general type of coupler, they're still coupling between component models of an Earth system model. So it would still be between an atmosphere and an ocean model or an atmosphere and a land model, something like this. And part of why I mentioned that they can become very complicated, and part of the reason is because each of these component models that want to use this coupler might have different like physical schemes that they use internally, and each of these schemes may require different fluxes that they need from the boundaries. And so you're right that this becomes a very complicated problem very quickly, where you can implement one coupler that works for one set of physical equations that are being used in the atmosphere, but then another model could come in that's maybe more has higher resolution dynamics that need more specific quantities or something like this. And then you have to add in capability for that in the coupler.
Amazing, thanks. Yeah, I think now it would be great to have a little 10-minute break so that everyone gets a refreshment. So exactly.